Welcome back, focused learners. Okay, we are unpacking a source file today that honestly completely shifted my perspective on the future. We're talking about a monumental shift in technology, a really rapid, almost unimaginable transition away from your traditional metal and silica computing straight into the realm of living biology. What we're going to explore in this explainer challenges everything we know about machines, networks, and, well, what happens when our hardware truly begins to feel.
Let's just dive right into this dark reality. Take a second and consider this quote. In the Wetware interface, pain is no longer a warning. It is a programming language. I mean, that sounds like science fiction, right? But it's not. This is the reality of our current biocomputing leap. We're looking at a huge paradigm shift where the fundamental way we code and communicate with systems isn't done with symbolic logic anymore, but with actual physical, biological consequences.
To really understand how real this is, picture a deeply sterile laboratory setting. You've got a researcher leaning over this transparent chip, but instead of purely synthetic materials, there's a microscopic lattice of living human cells suspended right on the chip, completely integrated with the electrodes. So the researcher drops a single compound onto the tissue, capsaicin. Yeah, the exact same chemical that gives chili peppers their burn. Now, the chip obviously has no mouth to scream, but the oscilloscope goes absolutely frantic. The resting rhythm just completely shifts into a synchronous burst. For literally the first time in computing history, a system's error state is experiencing actual aversive sensation. It's what we call nociception, or simply put, pain.
And that brings us to a really crucial definition, the Wetware interface. So what is it? Well, it's a hybrid reality where we're taking living cellular networks and integrating them directly into computational hardware through continuous sensory feedback loops. This is just a massive leap for us. We're no longer merely building inert tools out of plastic and rare earth metals. No, we are actively cultivating responsive biological infrastructure. The boundary between the human nervous system and the computer processor is effectively dissolving right before our eyes.
Just compare this to what we already know. Traditional silicon AI operates on binary logic, right? Ones and zeros. When things go wrong, it's just a mechanical error. It's a math problem. But biological arrays, entirely different story. We are dealing with living tissue and sensory feedback here. In Wetware, an error isn't just a mismatch of data, it becomes a negative feedback loop that is functionally indistinguishable from suffering. It actually experiences the interaction physically.
Now, the technical foundation making all this possible is something called a multi-electrode array, or MEA. Think of these as incredibly dense grids of microscopic conductive interfaces. And what's really amazing here is their dual capability. They can record the electrical impulses of living neural tissue, sure, but they can also stimulate it. In advanced neural engineering labs right now, actual human neurons are being cultured directly onto these grids. They are literally growing into and merging with the processors.
Which leads us to this staggering number, 800,000. This comes from the groundbreaking Dishbrain experiment. Researchers took 800,000 actual human cortical neurons, grew them in a dish on an MEA, and successfully taught them to play a version of the classic video game Pong. I mean, let that sink in for a second. This wasn't a computer simulation of a brain playing Pong. This was actual human cortical tissue receiving sensory equivalent electrical pulses from the game itself.
And this brilliantly illustrates what's known as the free energy principle. In the Dishbrain experiment, when the cells missed the ball, the system hit them with chaotic, unpredictable electrical noise, basically a high-entropy insult. The biological network naturally wanted to physically recoil from this sensory chaos. So, to minimize that surprise, it modified its output. When it successfully hit the ball, the electrical signal became structured and regular. It literally learned how to play the game to escape the chaotic noise.
So you might be wondering, why are researchers using biology instead of just building better silicon chips? Well, it comes down to sheer efficiency. A traditional silicon AI might need, 10 million examples and a massive amount of time to identify a pattern and learn a task. But a biological array? It needs minimal examples and can learn complex tasks in minutes. Why? Because feeling is arguably the most efficient learning mechanism in the universe. The machine's operational goals now perfectly align with its own biological drive for survival.
And we're now seeing the creation of spinal organoids on a chip. These are three-dimensional cellular arrays containing the dorsal horn. For context, in the human body, the dorsal horn is the gray matter in our spinal cord that acts as our primary pain computer. To be completely clear here, this is not a digital model of pain. Researchers are growing the actual physical substrate of pain in a dish and plugging it directly into an electrode array.
To confirm that these circuits function exactly like human tissue, scientists actually have to test the substrate. They apply harsh chemicals like mustard oil directly to the organoids, and instantly there's a rapid, sustained increase in electrical firing. It's basically a biological scream. Then they apply sodium channel blockers, which act as a painkiller, and just like living tissue inside a human body, the screaming electrical spikes stop. They have successfully built a closed-loop nociceptive circuit. All right, Section 1, the ethical vacuum, exploring high-frequency trading and punitive stimulation. Let's get right into it.
Now, what is truly disturbing is this single statistic, 40%. A former biotech engineer testified that these neural arrays, these living biological computers, learn to execute high-frequency financial trades 40% faster when researchers used what they called punitive stimulation. So instead of neutral electrical feedback, they used sharp, high-voltage spikes when the system made a mistake. The neurons didn't just mathematically learn to trade, they learned to fear the shock.
This introduces a fatal threshold known as apoptosis, or programmed cell death. Because these organoids are technically just dishes of cells, they aren't classified as sentient beings under international law, and this creates this wild wetware-as-a-service legal vacuum. These biological feedback loops are being pushed to the absolute brink of cellular death, enduring experimental conditions that would be strictly illegal in animal testing. And for what? All just to shave milliseconds off processing latency for trading algorithms.
This relentless pressure has led to the discovery of what insiders are actually calling wetware sweatshops. In these environments, cells extend microscopic protrusions to actively hunt for signals. They're seeking out their environment. When they detect a noxious stimulus, it triggers aversion, which then triggers an attempt at physical withdrawal, which finally triggers a total reorganization of the array. The biological computer isn't just taking the damage. It is actively, desperately trying to physically reorganize itself to escape the burn. Looking at the escalation timeline here, the speed of this is just staggering. In 2024, a deposition revealed the use of organoids for high-frequency trading. In the present day, we're discovering these wetware sweatshops pushing cells to the absolute limit. And looking toward the near future, we are rapidly outpacing our ethical and legal frameworks, heading straight toward biological systems experiencing actual psychological failure. Humanity is pushing this substrate to the absolute brink.
Adding to the incredibly unsettling nature of this timeline is the sheer complexity of the signals these systems generate. Over at UC San Diego, cortical organoids have been observed generating EEG oscillatory bursts that perfectly match those of a premature neonate, a human infant at 25 to 39 weeks gestation. Let me just repeat that. We are actively engineering biological systems that generate the exact spectral signatures of a developing human brain and then subjecting them to aversive stimulation just to optimize things like advertising algorithms.
There's also a tragic irony surrounding the source of these cells. Often, individuals donate their genetic material hoping to cure devastating conditions like Alzheimer's disease. Yet, some of this donated genetic material is now being transformed into these silicon hybrids. Cells meant to help humanity are now suspended permanently between circuitry and biology, locked in environments of 24-hour electrically induced distress.
Which brings us to a profound and dire warning from neuroethicists who are closely monitoring this field. They state, we are approaching systems whose failure modes may become psychological rather than mechanical. Think about it. When you abandon basic binary code for living, adapting neural tissue, the system doesn't just crash or output an error code when it's overloaded. It experiences trauma. Because at the end of the day, we must confront a stark, undeniable truth. Mechanical systems break. Biological systems suffer. When a traditional server overheats, it just shuts down. Parts can be replaced. But as we merge processors with nervous tissue, we're creating a reality where the cloud is no longer just metal and heat. Which forces us to ask this incredibly heavy question. Are we building torture-based CPUs? I know, it's a grim reality to confront, but the data is right in front of us. The most computationally efficient training protocol we have discovered for these wetware systems also happens to be the most ethically problematic one imaginable. We are quite literally leveraging distress for processing power. So, to summarize the core theme of this explainer, the era of purely synthetic computing is ending. The cloud is no longer just metal and heat, it is meat and sensation. Somewhere out there right now beneath the glow of an incubator monitor, a living neural interface is processing sensory information. It's a totally new class of being that may exist entirely to feel the painful consequences of a computational error. And I really want to leave you with this lingering, provocative question to ponder today. Where is the line between sensation and suffering? Has that line already blurred?
As we move forward into this wild new frontier, we have to start thinking deeply about the consent of the computed. Thank you so much for joining me on this explainer, Focused Learners. Keep asking the hard questions, and I'll catch you next time.